Now let's take a look at step 3, which is determining our optimization equation. Again, with this first question, we have a box using 108 square feet of surface area. We want to maximize its volume. It's an open box. We've already done step 2, which is determining the constraint equation. Again, that's based on your limited number of resources. In this case, you only have 108 square feet of box to work with, or cardboard. So the question now is, how do you determine the optimization equation? Well, actually, I think it's easier than a constraint because, again, if you go back and look at what you're trying to optimize, you want to optimize maximum volume, so your optimization equation will involve volume of that box. Now, the volume of an open box is the same as the volume of a closed. You can still fit the same amount inside of it. We just need to figure out the volume of this box. Now, remember, the volume of a rectangular prism is length times width times height. So it'll be x times h, or x squared times h. Therefore, for step 3, when we are determining our constraint equation for this one, let me erase these arrows. It will involve volume, which is what, determining the optimization equation, it will involve volume. In this case, it's x squared h, what we're optimizing. So again, I think that determining the optimization equation is actually a little bit easier than a constraint because we know we're trying to figure out maximum volume, so it'll involve volume. And now you're thinking, okay, why did we determine a constraint equation? Well, look how many variables we have in this. We have 3, v, x, and h. What we can do is we can use our constraint equation to make this in terms of 2 variables, which, just like related rates, is going to make it easier for us to take the derivative and figure some stuff out. You might be thinking, well, how does the derivative come into play? Well, go back and think about absolute min and max, okay, and relative mins and maxes, okay. Remember, we're talking about the greatest and the least amount. Those are absolute mins and maxes on a particular interval, so that's why we're taking the derivative. So that's it for this optimization equation. It just involves volume, since we're trying to find the maximum volume we can make from a box with 108 square feet of cardboard. Look at example 2. Again, we're trying to optimize, in this case, a minimum total area with these 2 shapes, a triangle and a square. We've already come up with the constraint equation, again dealing with the amount of material we have. This could be sticks or wire or something. We can easily figure out what the optimization equation might look like, because we were trying to have a minimum total area. So we just need to figure out the area of these 2 shapes, where area of a triangle is 1/2 base times height, so it'll be 1/2 x times h. And then over here, this area is y squared, y times y. Now, fortunately, we can use some right triangle, we can use the Pythagorean Theorem to figure out what h is in terms of x. And we will need to do that because we don't need an h if we can write it in terms of x. We want to use the least amount of variables possible. The total area would be 1/2 base times height of that triangle. The other one's y squared, as we said, easy. So it's 1/2 x times h. But how do we figure out h in terms of x? Well, go back and look at this triangle, this right triangle. The bottom would be 1/2 x. This would be x. This would be h. So h squared plus 1/2 x squared equals x squared using the Pythagorean Theorem. So that's exactly what we're going to do. We're going to have 1/2 x squared plus h squared equals x squared. Get h by itself. This will become 1/4 x squared. We will subtract 1/4 x squared from both sides to get 3/4 x squared. 1 minus 1/4 is 3/4. Then we will take the square root of both sides. Unfortunately, I didn't have room to show all this, but you can see it here. The square root of 3/4 is the square root of 3 over 2x. So h is square root of 3 over 2x. And again, since the area is 1/2 base times height, it would be 1/2 x times square root of 3 over 2x. So the area of that triangle will be 1 times square root of 3 is the square root of 3. 2 times 2 is 4. X times x is x squared. So the area of that triangle will be square root of 3 over 4 x squared. Will be the area of this triangle. Square root of 3 over 4 x squared. Pretty interesting. I never really thought about that. That's the formula for the area of an equilateral triangle with side lengths x. So there's the area of the triangle. There's the area of the square. This is our optimization equation, and again, it's optimization because we're trying to use those 10 inches. Yeah, we're trying to use the 10 inches of material that we have to create the least amount of area. So again, you can kind of see that we have the same variables here. Since we have two equations with two variables, we can eliminate one of these and then optimize to figure out least amount of area. So that's why we have a constraint and an optimization equation. All right, so let's go ahead and take a look at step 3 for our apartment building. What is an optimization equation for this question? Well, again, we're trying to maximize monthly profit, so our equation has to involve that. And again, this is by far the more challenging of the three problems. I'm going to be very thorough in explaining this. So let's say that our total monthly profit let's say that our total monthly profit, we're going to call it P. Now, how can we use, we need to use the same variables up here in our optimization problem. Well, up here we had N and R. So number of occupied units is equal to 30, total number of units minus vacant units, and we figured that out to be R minus 1,000 over 40. So this equation has to involve N and R. Well, again, I broke this down into words for my optimization equation for step 3. I know that the total monthly profit is equal to the total number of occupied units times the profit per unit. So for example, let's say I have 28 units that are being occupied, and I'm making $100 per unit. That would be $2,800 that I make in a month. Okay. In order to get profit per unit in terms of rent, I have to take whatever money I'm receiving for rent and subtract $120 in maintenance cost that they gave us in the problem. Okay, so if we subtract the maintenance fees from the rent, that will give us how much the building owner is making each month. So let's say rent is $1,100 a month, or actually, we'll just round it to $1,100, doesn't matter. It costs $120 to maintain that, so that would be $980 profit for that unit. And if we multiply that by the total number of occupied units, that will give us our total monthly profit. So here we have our optimization equation. And again, it's very important that the two other variables occurred in our constraint equation. That way we can use the constraint equation to get this equation in terms of two variables. Eliminate one and then take the derivative. That's it for step 3. That is our optimization equation for total monthly profit. Next, we're going to look at step 4, which is combining the equations into just two variables. Okay, we want to turn the optimization equation to two variables. If you have any other questions about the optimization equation or the constraint equation, even let me know.